All right, it's the last week. This week we're going to be reviewing writing and analyzing linear equations from data. So if you recall, linear equation in slope-intercept form is y equals mx plus b, where where x is your input, your y is your output, m represents the slope or the rate of change, and b represents your y-intercept or your starting value. So this should be fairly simple at this point. Identify the slope and y-intercept of each line defined by the following equations. So the slope is always the coefficient of your input, or the coefficient of x. So the slope here would be negative 1/2. The y-intercept would be 5. The slope in the next one would be 4/3, and the y-intercept would be 3/7. And the slope in the last equation would be 2.55, and the y-intercept would be 1.79. That's fairly straightforward, fairly simple. But what happens when you have a set of data? All you're looking at are the inputs and the outputs. How can you determine the slope and the y-intercept so you can write your equation? Well, one way to find the slope is to calculate it using the formula. When you are in a table, you could just kind of find the difference between adjacent points. If we look at y, how is y changing? Y is moving up by 3, increasing by 3, increasing by 3. X is increasing by 2, x is increasing by 2, and by 2. So it looks like our rate of change is 3/2, or 3/2. As y increases by 3, x increases by 2. And the y-intercept, if you recall, is always the output when the input is 0. So here the input is 0, the output is 5. So our y-intercept is 5, and our slope is 3/2. Once we've identified a y-intercept and a slope, we can write the equation that models this data. And that would be y equals 3/2 x plus 5. And sure enough, if you start plugging in these x values, you'll get out these y values. And that's that. So let's take a look at another table. All right, pause the video and see if you can write the equation of the line yourself. Pause the video now. Okay, let's see how you did. So here y is decreasing by 2, decreasing by 2, decreasing by 2, and x is increasing by 4, increasing by 4, and increasing by 4. So it looks like the slope is -2 over +4, which reduces to -1/2, or -1/2. The y-intercept here, where x equals 0, all right, if our input is 0, the output must be our y-intercept, so the y-intercept here is 8. So if the y-intercept is 8 and the slope is -1/2, we can write our equation y equals -1/2 x plus 8. That seems simple enough and pretty straightforward. However, what happens if all we have are 2 points on a line and no y-intercept? Well, what can we do? Well, remember, you have to identify the slope and the y-intercept. So as long as you have 2 points, a minimum of 2 points, you can calculate the slope using the slope formula. So let's do that now. y2 minus y1 over x2 minus x1. And that gives us a slope of 2. So now that we have a slope, we need to find the y-intercept, but all we have is a slope and some points. Well, luckily, we have the slope-intercept form of a linear equation, which has 4 variables: an output, a slope, an input, and a y-intercept. And we know that we can solve equations for one variable. We can't solve equations for more than one variable, at least not right now. So how might we go about doing this? Well, if we can plug in a slope, an input, and an output into this equation, then we can solve this equation for the unknown b, the y-intercept. Luckily, we have a slope, and we have an input here and an output here. We also have an input here and an output here. So what we can do is we can take our y equals mx plus b, plug in our slope, which is 2, plug in an input x, 3, plug that into x, plug in an output into y, 5, and now we have an equation that we can solve for b. 2 times 3 is 6, and subtracting 6 from both sides gives you b equals -1. So now our y-intercept is -1. Now, if this works for this input and output pair, it should work for the other input-output because they're both on the same line. All right, so if we plug in these values into the model, we should get the same y-intercept. And sure enough, that's exactly what happens. So once we do this, we've identified our slope and our y-intercept, so we can write the equation of the line y equals 2x minus 1. All right, here's another example with two new points, 2, 8, and 4, 19. Why don't you pause the video and try deriving the equation of the line on your own. Pause the video now. All right, let's see how you did. So did you calculate the slope to be 11/2? Good for you. All right, now that we have the slope, we're going to use a slope and an input-output pair to find the y-intercept. So the first input-output I'm going to use is 2 and 8. So I'm going to plug in my slope, my input 2, my output 8, and then I'm going to solve for b. So multiply by 2, simplify, subtract, and I get b equals -3. Now just to check myself to make sure that it works, I'm going to do the same thing for my input and output here. So I'm going to plug in my input of 4, my output of 19. All right, solve the equation, and I get, sure enough, b equals -3. So now that I have a slope and a y-intercept, I can write the equation of the line, which is y equals 11/2 x minus 3, or because this is it can convert to a simple decimal, you could write y equals 5.5x minus 3. And there it is. So let's use this to analyze situations that can be modeled by linear functions. So here's a situation. Monica feeds her dog the same amount of dog food each day. On the third day, she has 44 cups left in the bag. And on the 11th day, she has 28 cups left. Create a model based on the data. Then use it to determine how many cups of dog food were originally in the bag. According to this model, when will Monica run out of dog food? So the first thing I want you to do is create a model based on the data, and the data is contained in the problem, and you have to organize it the right way to get the right answer. So organize your data either in a table or a set of ordered pairs, and then create a model based on the data and try to answer the questions. Pause the video now. All right, let's see how you did. So this is what I came up with. The slope and the y-intercept can be derived using the information points from the problem. So I created two ordered pairs, 3, 44, and 11, 28. 3 represents the day of the month, and 44 represents the number of cups of dog food that were left in the bag. All right, the day of the month, or the time, is our independent variable here, and the amount of dog food left in the bag is our dependent variable. Some students have a tendency to kind of switch these up. So if you did that, don't worry about it. You realized your mistake, switch them back and rederive your model. All right, and I did the same thing here. On the 11th day, there were 28 cups left in the bag. So now I have 2 points. From these 2 points, I can use the method previously discussed in this video to derive the equation y equals -2x plus 50. Now, what does the slope and the y-intercept tell us about this? Well, the y-intercept gives us the initial number of cups of dog food in the bag, which is the answer to one of our questions. All right, use the equation to determine how many cups of dog food were originally in the bag. Originally in the bag means what was the starting point or initial value of our model, and that would be 50. All right, the -2 is our slope, and the -2 tells us how many cups of dog food are being used per day. All right, so we can use our model to answer the second question, when will Monica be out of dog food? So this is a question about our input, the time, not the output, the number of cups of dog food in the bag. because we already know that. If we're being asked when will Monica be out of dog food, we know how many cups are in the bag at that point. There's 0 cups. So if there are 0 cups of dog food left in the bag, we're going to solve the equation 0 equals negative 2x plus 50. All right, we set the output equal to 0 because we know there's 0 cups in the bag, and we solve for x, and that gives us x equals 25. So the bag will be empty after 25 days. This is an example of how a model can help you answer more complex questions about real-world data that can be modeled using linear functions. Let's try one more example. To ship a package, a company charges a one-time fee plus a fee based on the weight of the package. This table shows the total shipping costs for 4 packages of different weights. For part A, I'd like you to write an equation which represents the total shipping cost C in dollars of a package weighing W pounds. For part B, interpret that equation to determine the shipping costs per pound and the initial one-time fee. In part C, I want you to use the equation to predict what the total shipping cost would be for a package weighing 25.57 pounds. And finally, in part D, I want you to use the equation to figure out the weight of a package that could cost $40 to send. Pause the video and try this now. All right, let's see how you did. All right, write an equation which represents the total shipping cost C in dollars of a package weighing W pounds. So here we have a set of data. It's in the form of a table, but you could have chosen any 2 points and derived the equation using two sets of ordered pairs. Either either method would have worked perfectly fine. Either way, you can determine the slope, and then from there you could find the y-intercept. So you should have come up with C equals 1.5W plus 5. For part B, you're supposed to interpret the equation to determine the shipping costs per pound and the initial one-time fee. So the initial one-time fee is like our starting point, and that would be 5 or $5. The shipping cost per pound is our slope, or our rate of change, and that's 1.5, or in this case, $1.50 or $1.5 per pound. All right, for part C, use the equation to predict the total shipping cost for a package weighing 25.57 pounds. All right, this is a question about cost, and we're given a weight. So we're given an input value, and we're trying to find an output. So all we have to do is input our input and find our output. And that's exactly what you do. You input 25.57 pounds, and you calculate the total cost, which would be $43.355, or approximately $43.36. And finally, for part D, use the equation to find the weight of a package that could cost $40 to send. This is a question about weight, and we're given a cost. It is a question about W, and we're given the value of C. So we're given an output, and we're supposed to find an input. So we plug in 40 for our cost, and then we solve for W, the input. In this case, you get 23.3 repeating, or approximately 23 1/3 pounds. And that's it for this week. You've got 2 assignments, one on deriving the equation or a linear equation from data, and the other asks you to compare different linear functions represented through data in different ways.